Welcome to Pavonars, webinars for the pavement community. My name is Andrew Braham, and today I'm going to talk about establishing particle size recommendations for cationic asphalt emulsions. And this is based on work done by Turben, who achieved his Bachelor's of Science and Master's of Science, both from the University of Arkansas, and is currently pursuing his PhD here at the University of Arkansas. And also work done by Mr. Pedro Diaz-Romero, who also obtained his Bachelor of Science and Master's of Science from the University of Arkansas and is now a civil engineer with SGEC down in La Paz, Bolivia, and you can find his LinkedIn profile linked below in the description. Now, as I get going into the content of this Pavonar, please note that the paper this Pavonar is based on is available free for download. So I encourage you to download it because there are a lot of details in that paper that are really excellent to dig into to learn a little bit more about our decisions with these preliminary recommendations. Now, this is based off previous work, and there are two Pavonars available for that. The first is developing a particle size specification for asphalt emulsion, and this correlated viscosity to particle size for CSS and CMS emulsions. And then a little later on, we refined the particle size specification for asphalt emulsion, and we expanded our knowledge into CRS emulsions, both unmodified latex and solid polymer based. And we correlated not only viscosity to particle size, but also to the sweep test. CRS emulsions are a rapid set emulsion, and they are generally used for a spray application, for example, a chip seal. And the sweep test is a performance test that evaluates the chip seal performance with both aggregate and asphalt emulsion. And so this work is going to correlate the viscosity of particle size, the viscosity to particle size, and to the indirect tension and direct shear test for CSS emulsions. So kind of like our second paper listed above that looked at the sweep test compared to the CRS emulsions, this work introduces this concept of the indirect tension test and the direct shear test for CSS emulsions. So trying to get some performance tests behind our work. Now, a quick review here of what I mean when I say particle size. This is a very typical particle size distribution curve for an asphalt emulsion. And this is something that Tanner came up with. You can see US standard sieve sizes along the top x-axis and then particle diameter in microns along the bottom x-axis. So number 200 sieve is 75 microns. And you can see that particle sizes of asphalt emulsions are all essentially smaller than a number 635 sieve. So that's like the 20 to 30 micron range. And with these distributions, you can get many different metrics that you can try and quantify the distribution with. The first is D10, which is the particle size where 10% of the volume of your sample is smaller than that particle diameter. D50 or a median is the particle size where 50% of the volume is smaller and 50% is larger. D90 is the particle size where 90% of the volume is smaller. So you got your D10, your D50, and your D90. That all has to do with the percent of the particles in your analysis that are smaller than that size, particle diameter. Then you have the mean, which is the arithmetic average particle size, and the mode, which is the most common observed size. So these are all different ways to kind of see where along the particle diameter scale is your asphalt emulsion. Does it shift to the left a little more, or does it shift to the right a little more? Now we also have the width of the distribution, and you can quantify that by finding the standard deviation, which is the measure of closest to the mean, or the span, which is the measure of closest to the median. And the span can be defined as D90 minus D10 divided by D50. So those last two bullets there have to kind of do with the width of the distribution curve. And the first the first five bullets have to do with where along the particle diameter scale the curve is. So both very, very important ways to quantify your particle size and your particle size distribution. Now, there is no existing specification. If you take a look at, we're looking at cationic asphalt emulsions here. So if you take a look at AASHTO M208, there's no existing specification for particle size. And so what we did for the CSS is we looked at the direct shear test, and this measures the cohesion gain of, for example, a CCPR or a CIR, cold in place recycling or cold central plant recycling asphalt mixture. And this is actually based on the direct shear test for tack coats. So the apparatus is on the left. In the middle there, we have kind of a loading diagram where half the sample is on the left side, half the sample is on the right side, and you apply a load and it shears the sample in half. And there's some sort of shear plane that forms in the middle of that sample. And you simply measure the load and the displacement, and you quantify the peak load, as you can see on the example data plot on the right. And this is a way to measure how quickly the asphalt emulsion gains cohesion during the curing process. Well, we also tested just the simple indirect tensile strength over time. And you can see here, this is over 200 plus days. And we looked at a CSS1 and a CSS1H, so both cationic slow set emulsions, both low viscosity, and one is a hard pen asphalt emulsion residue. And you can see in general the IDT strength decreases over time. So as the asphalt emulsion ages, as it gets older, the IDT strength decreases over time after mixing and then measuring the indirect tensile strength. And the direct shear strength increases over time. Now these curves are a little rough, they bounce around a little bit, and we're just looking at the trend lines here and observing that over time, over these almost 20-day period, the shear strength actually increases as the asphalt emulsion has been sitting. So the indirect tensile strength decreases, the shear strength increases. And what this led us to do is allow us to kind of fill this recommendation to date of particle sizes. So you can see the CRS-2 was based on previous research. We have the D50 or the median. And for CRS-2, we recommend that be lower than 1.9 microns. Or you take a look at the mode, the D10, the D90, and the span. So there's kind of two ways you can approach this. We can just look at the median, the D50, or we can look at that collection of four that are below there, and you can see the four different values, 1.6, 1.1, 2.8, and 1. All those values have to be less than those I listed in order to be what we consider a good performing asphalt emulsion. And this has to do with correlating the viscosity specifications to the particle size and correlating the particle size to these performance tests. Here are the numbers for the CRS-2L and the CRS-2P. So you can see as you modify the binder or you modify the emulsion, the particle size recommendations increase, and they're quite a bit higher for the polymer modified asphalt binder, the CRS-2P, versus the latex modified asphalt emulsion, the CRS-2L. Now it is worth noting that the CRS-2L, that latex, is actually an emulsion itself, so we have an emulsion within an emulsion. So there's things going on there. These are just preliminary recommendations. This is just kind of our first. We think it's important to talk about particle size. This is what we observed. I hope other people start looking at it. I hope other people start challenging these numbers. And I hope over time we can come to a consensus as a community if this is important to pursue. The CMS, this is just looking at the particle size versus viscosity, and you can see it's less than 6.9 median or less than 3.2 D10. And then finally, we have some nice recommendations for the slow set emulsions too, the cationic slow sets. And you can see those listed on the right. And the hard pen values are a little higher than the standard asphalt emulsion residue, the CSS-1, except for the span. The span is the only value that's a little lower. So these are our particle size recommendations, and please note these are to date. There is more work to do. I think there's a lot more to uncover here. We just took a look at a handful of emulsions. We ran some tests in our lab. I think that these need to be replicated in other labs. I think there's a lot more to do, but I see this as a starting point. At least we can say, hey, do these numbers even make sense? Can we refine them? Are there better ways to refine them? Those type of discussions. So as I mentioned at the very beginning, this is a very, very brief synthesis of the full paper, which is establishing particle size recommendations for cationic asphalt emulsions. And as I mentioned, this paper can be found online free. You can download it, and the link to the DOI is below in the description. So I appreciate you joining me today, and I hope you have an absolutely wonderful day.